As David mentioned, I'm from Phase Change Energy Solutions Australia. Obviously, we know that we've got an energy problem. We keep burning up our resources, and it costs a lot of money, and we don't want to keep doing it. So, some clever scientists, probably about 30 years ago that I've heard about, were using phase change materials to try and stabilise temperatures. A phase change material is simply a material which takes advantage of a fundamental principle, and that is that it melts. If you take a block of ice and you put it inside a glass of Coke, what happens to the Coke? It gets cold. But what happens to the ice? It doesn't get hot, does it? Okay, that's the fundamental principle that we use in phase change material. The ice doesn't get hot, it just transitions. And it's the transition that all of the energy is used. So what phase change materials are is materials that absorb and release heat at predetermined temperature ranges. If we take ice and we put it in our home, and we take it out of the fridge and we put it in the room, it does keep us cool in summer, but it's too cold and it melts quickly. And it's no good to us in winter. If we melted something that was very hot, say steel, at 1,000 degrees, then it would actually also phase change from a solid into a liquid and absorb a huge amount of heat while it turns from a solid to a liquid. That's another phase change. Who can think of another phase change that happens almost every day in our work environment? Anybody? Air conditioning. The liquid that goes through the coils in the air conditioner evaporates into a gas, which is a phase change. And then we take it outside and we squash it back into a liquid again and release the heat outside. Okay, it's a phase change. If you take a pot of water and you boil it on the stove, it hits 100 degrees, it doesn't get hotter, does it? So it's absorbing heat without getting hot. It's another phase change from a liquid to a gas. So phase change is not a new idea. The new idea is that it can be put into a package that you can put into your building and it stays stable for a very long time. That's the challenge that's been out there for a very long time, is to actually make phase change material into a building material. So the engineers in the US thought, how will we do this? They looked at using salts, because if you put salt in water, it changes its freeze point. They looked at using animal fat, but they thought that would be socially unacceptable. If you look at the fish and chip shop and you go there, you see the solid mass on top of the fryer, and they heat it up and it melts. Okay, it's phase changing. You take soap and you heat it up, it'll melt in your hands. It's phase changing. You take chocolate and you put it in your mouth. What happens? Yeah, it melts. It's phase changing. Okay, so lots of things phase change. So they looked at salts and they looked at petroleum products such as paraffin wax. You take a candle and you heat it up. What happens? It melts into a liquid. It's another phase change. Some manufacturers in Germany, such as BASF, I think, and DuPont, developed phase change plasterboard. So they took plasterboard and they impregnated it with small balls of paraffin wax, candle wax, and they would put these plasterboard sheets on the wall and have an incredible building performance improvement. The dilemma with it is that if you cut paraffin wax, it smells like a candle. So you end up with a house that smells a bit like a candle, which is not always so pleasant. So they've actually, I believe they've taken it off the market. I'm not quite sure. The principle is good, but the delivery mechanism is the issue. So looking at phase change material here, we've got a plastic mat, which you've all got a sample of. Does anybody not have a sample of the phase change? Yep. One for you. And I'm going to pass them back to the back. Thank you. It's a plastic mat, and it's containing phase change material. If you have a look at it on a thermal imaging camera, you have a look here. This is a thermal imaging camera. Has anybody seen one of these before? You might have seen the movie Predator. Okay. He had one of these. He wasn't really seeing it. He just had a camera. A thermal imaging camera basically has a whole array of little tiny sensors called microbolometers, and they detect temperature. And there's a crystal lens there that focuses the heat on it, and then it turns that into a picture. So I've calibrated it to see cold to hot between about 20 and 35 degrees, which is why people are looking white, because they're above 35. If you take that sheet there, sir, and hold that up in front of the camera for me, you see the temperature of the mat is much cooler than the room. Now that mat was in Melbourne this morning on a concrete floor where it actually refroze itself. So it refroze itself using the night air. And that's the most clever thing about phase change material, is you've got free energy. Okay, because the energy that's stored in here is just the energy that we let go of last night when it cooled off. So we're kind of like Robin Hood. We steal from the rich and give to the poor. So we steal the heat, steal the cold out of the night and give it back in the day. Or in the cooler months, we steal the heat out of the day and give it back in the night. It's quite logical when you think about it. Does anybody here have a house with high thermal mass? Yeah? And how have you achieved that? Masonry. Yep. Anything? Anybody else?
Concrete slab.
Concrete slab. Okay. Concrete's a very good thermal mass. The dilemma with normal traditional thermal masses is that they have thermal mass properties all the way from -10 to the point at which they melt. And that's called sensible heat absorption. When heat is put into a concrete slab, it gets hotter. Now what happens on a really hot day with a concrete slab?
Gets really cold.
But it gets too hot eventually.
Oh, eventually.
Yeah, and then in the middle of winter, what happens to it? It gets too cold eventually. So you have to deliver a huge amount of heat into concrete to get it up to a point at which it's comfortable to enjoy. And then once it gets past that comfortable point, you've got to wait for it a long time for it to get back again. So sensible thermal mass is good, but it's got some downsides. When it's outside the comfort range, it's not our friend. It's a slab, yeah. But if you had a suspended slab and the windows, it doesn't get that hot, yeah. Yeah, but it does get cold in winter then. Yeah, okay. So the negative side of thermal mass is that it actually doesn't help us in the wrong time of the year. The difference with that and phase change material, any kind of phase change material, is it doesn't exhibit any thermal mass property below its melt point. So below 18 degrees, this is just like a lightweight piece of plastic with some vegetable fat inside it, which is what the material is made of. So that there is just like putting a piece of concrete this thick inside your house. The difference is that once it starts to melt, it exhibits a huge thermal mass. It's about 40 times more than concrete per gram. Okay, so that's how much more energy it stores than concrete. Concrete's about 1 joule per gram of material. This material here is about 40 joules per gram across the melt range per degree. So every degree it goes up, it absorbs 40 joules. Concrete, every degree it goes up, it absorbs 1 joule per gram. Water is about 2 joules per gram when it's water. When it's ice, it's about 400 joules per gram across a very tight band. Water is one of the best phase change materials you'll ever find. The problem is it freezes at 0. And we're not Eskimos, okay? We don't want to live in that comfort band. So this is effectively room temperature ice. So we'll go back up to here. So if you have a look here, we've got different phase change materials. So we can actually, by mixing different types of vegetable fat into the little pouches, we can get different melt bands. You can imagine that chocolate melts at a different temperature to coconut butter, for example. And we can get different masses. So the more kilograms of material you have, the more thermal inertia you get. It's kind of like a truck on the highway. If it's laden with weight, it'll carry a long way once you turn the engine off. The more mass you put into the house, the more thermal inertia you get. For example, in my house, I've got 25-degree phase change material upstairs, and during a hot day, the room slowly climbs from 19 degrees to eventually hit about 25, 26 degrees by the end of the day. Now upstairs it used to get to 35, 36 degrees. Now it doesn't get past about 26, 27 in the middle of summer. Overnight, I just open the windows up and the night air comes in, provided the night air is below about 22, and the night air will refreeze the material back again ready for the morning. And while it's refreezing it, I'm enjoying the room at 22 degrees because it's releasing the heat. So it doesn't have a negative effect on the comfort of the home.
This mainly in the ceiling.
Just the ceiling, yeah. I would love to have it in the walls too, but I don't want to pull my plasterboard off. Yeah, so if you want to go just ceiling, you can go a bit thicker. The thicker you go, the more thermal mass you have. You can't really put too much in. This is a church that got converted into a house. They put a lightweight extension on top. Lightweight extensions are great because they're inexpensive to build, and you don't have to worry about support for steel to hold concrete slabs up to get thermal mass, which makes your house comfortable. The problem is that you've got no thermal mass, so therefore your building swings in temperatures. If you have a building on a hot day with no thermal mass and you open up the doors and the heat comes in, then you close the doors, it doesn't matter how much insulation you have, it's hot inside. And you can't get it out unless you pump it out with an air conditioner. The difference is with phase change material, you open the doors on a hot day and you close the doors again, the material will suck all the heat out of the room and bring it back to 22 degrees again, depending on where it is in its melt cycle. So it's like an air conditioner, but you can't hear it, like the one you can hear up the back there. Okay, in the same way, in winter time, if you have a warm house, let's say you've got a fireplace going and you've warmed up the ceiling with the fireplace, and then you open up the doors and all the cold air rushes in, and then you close the doors again, the house heats up again because the ceiling is melted and it has to reset to a solid to release its heat. This is the principle of phase change material. It's basically just stealing the heat and giving it back when you need it, or stealing the cold and giving it back when you need it.
And not like concrete where if it heats up too much,
then it's a pain.
Time consuming.
You don't want it, exactly. So the good thing about phase change is if you've got a badly designed house, you still get a great benefit. In Melbourne, we have about 200 days per year where we don't have to heat and cool a house. I imagine it's probably fairly similar in Sydney. With phase change material, at my house, it's jumped up to about 300 days per year where I don't have to heat and cool actively. I can just steal the cold of the night and I can just steal the heat of the day and just give it back when I need it. And all I do is I manage curtains and windows. It's very simple. Hot day, close the curtains, close the windows. Night time, open the curtains, open the windows, let the heat out. So it's like a very, very slow air conditioner. I'm charging it in the day and I'm releasing it at the night. When I look at the middle of winter, I want to keep it all closed. So I'll keep the curtains open so the sun can come in and a bit of heat will charge the ceiling. But if I don't get enough from the sun in the middle of winter, I light my fireplace. Or I could run my air conditioner in reverse cycle mode in the middle of the day.
But you said that the air temperature has to be 22 degrees or below, not above. What happens on those hot summer nights where
That's a good point. Okay, and that's a good point. You can get onto the Bureau of Meteorology website, and David can help you with that if you don't know how to do it. And within it, you can actually put your region in, and you can tell it how many nights per year does the temperature not fall below 20 degrees. And you can count them. Okay, and you can say, right, there's 16 days here in Sydney where the temperature at night doesn't fall below. Those nights, the phase change material won't reset itself. Okay, then you could put more mass in so that you can get through 2 days. Okay, and if you might have 2 nights in a row where it doesn't get below 20 degrees simultaneously, you could have more mass and get through 3 days. It's quite possible to go through the entire year without actually having any heating and cooling if you have enough phase change material.
I just want to point out the thing that you referred to there. The thing to search for the Australian Bureau of Meteorology is heating days and cooling days, and that will get it. That will help you find it.
Yeah, that's right. So
Now you talked about putting the air conditioner on in the winter and the day to warm it up.
Yep, you can do that.
That's true at night. In summertime, you could use off peak after.
Yes, exactly. You can pre-freeze the house. In Queensland, what we're doing, we're talking with the Queensland government, and their dilemma is that people get home from work at 3 o'clock, because they're Queenslanders, so they get to do that. And they all put their air cons on at once because it's stinking hot and they had a hard day. Fair enough. The problem is the grid can't handle that. So they have to put a big grid in with a big power station to feed the power for that 4-hour window from 3 p.m. till 7 p.m. And that's expensive, which adds cost to the people, the taxpayers, and adds cost to the new land being released. So what we're doing in Queensland is we're using solar panels on the roof to run the air conditioner while they're at work, which is free electricity. Pump the heat out of the phase change material in the middle of the day, get it down to 20 degrees. They get home, turn off the air conditioning, and the house is pre-frozen at 20 degrees, ready for them to enjoy their night. So free cooling in Queensland. Okay, much better than paying for 38-cent shoulder tariffs and things they've got now.
What's better, if you had a flat roof, on the top of the roof, underneath the...
Okay, the question is, where's the best place to install phase change material? Closest to the people. So in between the plasterboard or the timber lining and the insulation itself. Because you're trying to control and stabilise the internal temperature. You're not trying to control the external temperature. You can in extreme climates like Port Hedland, Marble Bar, you can put phase change externally as well, and that'll resist the heat getting to the insulation in the first place, and the night desert air will refreeze it, so it will give it a better thermal property. But for the most part, you don't need to do it. You see here's a church that was done in Ashboro, North Carolina, where the temperature fell dramatically after putting phase change material in with new insulation. Huge energy savings. This is a very interesting graph. This really sums up what phase change material does. If you have a look here, the ambient temperature falls here down towards, say, what's this, 10 or 11 degrees over here overnight. It's a pretty typical cool night in maybe spring or autumn. And then it climbs through the day. Eventually it hits up here around 31, 32 degrees. With an insulated home, the insulated home lags behind the outdoor temperature because insulation just slows the transfer of heat down. So the heat transfers through, the house eventually gets cold, you've got to put a heater on through here, and then you get to here again and it gets too hot and you've got to put an aircon on through there, or you just put up with it, which is probably what some people do. With phase change material, here we're releasing heat, which is keeping you warm. So we're not getting below here 21 degrees or so. And then here we're absorbing heat, keeping you cool. So simply by using the natural process of melting and resetting, we can actually stabilise the building temperature. And the way that you do it is you simply use your windows and your curtains. It's that simple. And if that's not good enough, you can use your air conditioning on reverse cycle mode to pump heat in or pump heat out. A very small air conditioner can do an enormous amount of work. We have in my house, the living area is about 50 squares. It's quite big. I've got 5 kids. we used to use a lot of electricity. My electricity bill is about $1 a quarter. Okay, and that's thanks to solar power, which helps produce my electricity. It's also thanks to the fact that I hardly use any heating and cooling. But I do have an air conditioner there because I do like it cool on the stinking hot nights. So on those hot nights, I put my 2 kilowatt air conditioner on and I pre-freeze my ceiling overnight on off-peak rate to get it ready for the next hot day if the night is actually above 20 degrees. This summer, I think I used the air conditioner 4 times to do that. So a single 2 kilowatt air conditioner, I used it 4 times across summer.